Hi, this video is really introducing the core science behind food sense generation 4. So food sense generation 4 is intended to measure the hotness of chili products, but we do that actually through the measurement of capsaicin in those samples. So I just want to jump into it a little bit about the actual science, because with the food sense generation 4, we say that we can do a kind of qualitative determination that this actually is capsaicin, and I'm going to show you the real sort of electrochemistry behind that signal. And it's also the quantification, that the intensity of the peaks that I will discuss, how high they are, is actually telling you how much capsaicin is actually in there. But I want to run sort of the science of that. So if you have a food sense generation 4, it's quite attractive, fits in the palm of your hand, so it's quite a small device. But in the front of it is a electrochemical sensor. So this sensor is for capsaicin. So let me dive in a little bit more on that. This is what the sensors look like, and then I'll zoom in a bit more on this. If you're interested in food sense in general, then there is a website for that, foodsensetechnology.com. But let me go forward a little bit more and say here is this is the chili sensor. And if I zoom in on that, we have these electrodes. So this is something that we manufacture at Zimmer and Peacock. And I will be zooming in a bit more on this. Now, if you're a client of ours, we always kind of give training and lots of information. We try to say, look, what you do is, in the end, you pipette 50 microliters of the sample onto the sensor. But once you've done that, I want to talk about what's actually happening here. Just a way of background, and I think this is kind of more just for history, really. This is Professor Richard Compton. So he wrote one of the original papers on this electrochemical determination of capsaicin. He's at the University of Oxford. I think he's at St John's College, Oxford, UK. And this is obviously the structure of capsaicin, and this is the molecule that we're actually determining. Now, he's an electrochemist, so this assay is an electrochemical determination of capsaicin. But if you're a client of ours, when you run the assay on your smartphone, you will get a Scoville heat unit. You'll get a number in the units of Scoville heat unit. But actually, all the raw data goes to the cloud. And so for kind of, I want to say more advanced users, but for some people, they actually want to see the raw data. This can be very useful for sort of transparency, that you get a number, but where did that number come from? And actually, there is all raw data goes to the cloud, and later on you can log in and actually find that raw data. But I want to explain what are you looking at when you are potentially looking at that raw data. So you don't have to look at these signals, but if you choose to look at these signals, why do they look the way they do? So we say the food sense generation 4 is both qualitative and quantitative. So when by qualitative, it generates, when the assay is running, it generates a series of peaks. This is peak 1, and I will have some slides explaining peak 1. This is peak 2, and I will have some slides explaining peak 2. And then we do what's called a second scan, and we get a new peak, and we call it peak 3. So this is very, almost like a fingerprint for capsaicin, and I want to explain really where it comes from. And I want to also explain that the peak heights are proportional to how much capsaicin is in that sample. So if the peaks are very intense, it's hot, and if the peaks are much smaller, then it's mild. It's that simple, but it's more than just qualification like that. It's actually quantification as well. So let me go forward a little bit more. So I said there's peak 1, peak 2, and peak 3. So let me start with peak 1. So we have our electrochemical sensor. We have our 50 microliters of sample on that sensor. And this is the capsaicin. So the sample has capsaicin in it. And we have here what we call an electrode. That electrode has a potential applied to it. Now, potential has the units of voltage. When you apply a potential to a molecule like capsaicin, capsaicin is what they call redox. It's got reduction and oxidation properties. And when we apply that potential, it oxidizes. So capsaicin oxidizes. So you'll see in a minute that it becomes a new what's called a cation radical. And I don't mean to use the chemistry terms, but we have to dig into what the science is of this. So what happens here is we've got this molecule, and it gets oxidized, and we form what's called a cation radical. So this position here becomes a cation. Now that cation is, the formation of this cation rather, is the first peak you see in the voltammogram. So what I'm going to do is I'm going to let this simulation go back to the very beginning, but on the first scan you will see peak 1 form. Peak 1, by the way, is is labeled at peak 1 here, but when you're running food sense generation 4, you get a progress bar. So what's it doing? The first thing it's doing is running, and in the background it's recording this, so it actually records that peak. That is peak 1. So the question now is, where does peak 1 come from? And it's probably worth saying that peak 1 comes from the oxidation of capsaicin. Now there's something else that happens at this point as well, because we've just formed what's called a cation radical. Cation radicals are reactive, and the sample is full of water. So there's actually what we call a hydrolysis. Hydrolysis just means water, and lysis means bond breaking. So water is breaking some bonds. So the cation radical reacts with water, and we actually form what's called a quinone. This is significant because this quinone was not in that sample when we started. Capsaicin in peak 1 was oxidized to the cation radical. The cation radical is reactive and reacts with water, and now we formed a new molecule called a quinone, and this is the new quinone. So this is new and wasn't in the sample at the beginning, but it's significant for giving us this distinctive peak 1, peak 2, and peak 3 shape. Now in peak 2, we have a quinone that we change the potential to what we call E2, and the quinone undergoes what's called a reduction. So there are some groups here, double bond to oxygen, double bond to oxygen. These get reduced, and that becomes a single bond to oxygen and a single bond to oxygen, and we've got some hydrogen atoms on here. So we call this a reduction. And that reduction is what actually gives us peak 2 here. So as it comes around, so what I'll do now is I will let this simulation essentially get back to its start, and I'll describe again what we're seeing. So this is the qualification in the first instance, that this is capsaicin. Here's the oxidation of capsaicin to give a cation radical, which then undergoes hydrolysis. Having it undergone hydrolysis, it's got this quinone. This quinone gets reduced to what we call a quinol at this point. So that's where that peak comes from. It's a reduction of quinone to quinol. I'm just going to slightly shift that quinol to the surface, because there's something that's important that happens here. The quinol, which was formed as an oxidation of the quinone, sticks to the surface. It's really important, because people try to then think, oh, I can reuse these electrodes. You can't. These molecules are binding to the surface, and they're not going to leave that surface. So the sensor will work and quantify and qualify that this is capsaicin, but the capsaicin ends up sticking to the surface. So if you try to reuse the sensor, you will get increasingly stronger answers, increasingly higher concentrations. And it's because every time you run an assay, a certain amount of capsaicin sticks to the surface and adds to the signal the next time you run a sample. So you cannot reuse these sensors, and it is literally this step here where the quinone is reduced to the quinol, and it's now stuck to the surface. Now I want to describe what we call peak 3. This is the last peak that tells us that this really is capsaicin. So now I'm going to discuss peak 3. So we've got our quinol that was formed in peak 2 from the reduction of quinone to quinol. And in peak 3, we change the potential to E3, and we oxidize quinol back to quinone. And so when you're looking at this simulation, peak 1 was due to oxidation of capsaicin. Peak 2 was due to reduction of quinone and to quinol. And now peak 3, which is here, is the reoxidation of quinol to quinone. And that's why we've got these 3 distinctive peaks. And if you're a client of ours, you will be using the instrument. You'll get your Scoville heat units on your phone, and you're happy with the number. But for some clients, they need traceability. They need to have evidence of where that number comes from. And they will actually, any one of you who's a client, you have a cloud account which you can log in using your username and your password, and you can see the raw data. And so when you're looking at that raw data, I want you to have a little understanding of where that raw data comes from. So I've said that we can qualify, or that is capsaicin from those very distinctive peak 1, peak 2, and peak 3, and you will see them in your cloud account. You don't need to look at this. You can actually just take the number off the phone. But now I want to talk about the quantification, that actually the method that we're using is voltammetry, and the peak heights that we're getting are indicative of how much capsaicin is in here. So we have here a super low concentration of capsaicin. So we have signal versus concentration. Now we put in some more capsaicin and the signal increases. Now we put in some more capsaicin and the signal increases. Now we put some more capsaicin in and the signal increases. So the signal, or the peak height, is proportional to how much capsaicin is in the sample. So that is why I can say it's a quantitative technique as well as a qualification, that this really is capsaicin as well. So I will just go to the aim of this was to do qualification and quantification. The food sense will do all of this automatically for you, but if you find yourself having to understand where this signal came from, then I hope that some of these slides actually help with that. And so if you've got any questions for ZP, don't hesitate to contact us. Okay, thanks very much.